is more qualitative. So let's try and understand also some of things a little better. Okay, so let's get started. And initially, I'll just have a quick recap of what we had done yesterday. And just see, sometimes when we revise some of the things, perhaps we understand little better. Okay, so let's see that part. See, just again, let's go through this part. I think the part of sign convention. Okay, see, I think this part is easy to should be easy to understand if we have certain arrangement of current carrying elements. Okay, so it creates certain field. So suppose field is something like this. So whatever field, and field doesn't depend on kind of loop we choose. So when we take this for some field exists, I think it should be easy for you, most of it, to understand. Whatever, if I calculate, suppose this is force, if I calculate the line integral, which is dot product between field and displacement in one direction, if I get a positive value, some value x in the some positive value, if I change everywhere, whatever value I got, I'll get the negative of that. So if I go in other direction, so if in anti-clockwise I get a value of line integral as plus x, if I go in clockwise direction, it will come as minus x. So line integral value depends on direction in which we traverse the loop or move around the loop, similar to displacement. So it may be positive, it may be negative, depending on which direction we choose. So if the left hand side of the equation is this, so this term can become positive, negative. But if it is positive and anti-clockwise direction, it may turn negative if we check clockwise direction. So this term depends in the which direction we move, and according, if this term changes, right side also should change. So how we should have, so depending on which direction we traverse, the sign convention of current also what we take also should change. So whatever arrangement is mentioned here to make sure that these two are consistent. So that's why when we choose the direction in which we take the line integral, we also define which direction current is positive, which direction current is negative. So whole purpose of defining that is which is positive, which is negative, and we can choose a particular direction, calculate BDL, and then we choose. So I hope in this particular case it is clear. If we choose line integral of resultant magnetic field along curve plus, okay. So when is positive, when is negative. So understanding of logical reason why sign becomes important here, just to make sure that left hand side and right hand side are consistent with each other. Then some application part. Okay, this figure application part, similar. There is some similarity with Gauss law. So there also, to apply Gauss law, we take a closed surface. To apply Amperes law, we take an open surface. What is open surface? Open surface can be plane or curved, and any open surface will have a boundary. The boundary of open surface is called a loop. Okay, so in this particular case, if I have to find field at a point P due to infinite line current, infinite current, I choose an Ampere loop. Ampere loop is I choose an open surface which is in form of a circle, point P lying on the perimeter of the circle, and boundary of the circle forms a boundary of circular shape forms a circle. Boundary of a circular open surface forms a circle, dotted circle. So when we take this Ampere loop, and if this is 3 dimension, if you view from the top, this is how it looks like. And if it is dot, we know from right hand cross rule, the direction of field will be something like this. And if we traverse the loop in this direction, if we traverse this loop in this direction, the direction of current, this becomes positive. So what will happen? The left hand side also will become positive, right hand side also will come positive. Had we taken other direction, what would have happened? The angle between B and DL would have been 180 degree. The line integral would have become negative. Even the current also would have taken negative. So it does not depend which direction we choose. Both the direction, the result comes to same. So in this case also, we take line integral everywhere cos theta is equal to 1. Hence B dot dl, if we integrate over the entire circular loop, it comes into B into 2 pi r equal to mu naught into I. Not a simple thing, we understood. Slightly more extension of this, I hope you understand what does this imply. So before I do this one, I'll do one more thing. I think we have not done it before, but many times we don't discuss. What does we mean by long or infinite? Let's try to understand what does infinite mean. There's nothing called infinite. Let's understand whenever we talk about law infinite, what does it signify? So I'll take up with one example, try to understand what does infinite mean. And just it's again not very essential thing, but if you understand is good. See, let's take, suppose we have a wire. It is not infinite. Okay. If it is not infinite, if we have to calculate field at point P, then what will the field will be equal to? Field is equal to mu naught by 4 pi I by d sine alpha plus sine beta. Suppose I want this field to be 90. What should be the length of the wire? This distance is d. What should be the length of the wire here? And this point is symmetrical. So that field is equal to 95% of the field due to infinite wire. This statement, do you follow what does this statement imply? So there's certain length of wire. If I take infinite wire, I get a field B. So what is the length of the wire should I take so that the field created at this point is 95%? What has to happen for that condition? How would this become 95%? See, if it is infinite, sine alpha is equal to 1. For field to be 95%, what has to be value of sine alpha? 0.95. If length is such, if this angle is equal to alpha is such, the sine alpha is equal to 0.95. Then I'll get a field which is 95% of the infinite current element. And what is the alpha for that comes to? Alpha comes to a sine of 72 degree is roughly equal to 0.95. And tan of 72 is equal to roughly 3. So what does it mean? Suppose this D is equal to 2 millimeter. What is the length of the wire I need to have a field which is 95% of the field due to infinite length? Can you someone think of, can you put this figure together and work out what should be the length of the wire?
12 millimeter.
Yeah. So this is 3 times of this. This is 2. It means this side also has to be 6 millimeter and this also has to be 6 millimeter. So you understand, even this 12 millimeter of wire will create a field equal to 95% of the infinite length. So as long as I'm going for approximation, can I take even, see, if I'm not very, if my tolerance limit is 5%, can I take even 12 millimeter also is infinite? Almost. And suppose not 12 mm, if it is 20 mm. So can it be taken infinite?
Yes, sir.
So you understand the significance, but this is something, the length which is required. So even if I have 10 meter length, so not 12 millimeter. So suppose I have length of 10 meter. What is the effect of the remaining part of the wire? Remaining part of the wire, 12 mm is creating 95% of the field. If length of the wire is 10 meter, what is remaining close to 10 meter doing? All remaining 10 meters only creating 5% of the field. So when we create which part is dominant, the effect of part of the wire, which is close to the point, has a much important part. Rest of it has lesser contribution. That's why I think this we talk about infinite, it makes some sense. So what does it mean now? So let's see, let me extend this point further. So suppose I have a wire which is not 12 mm, let's say this wire is 20 millimeter long. And I choose one point here, something which is at a distance of from this end 5 millimeter, this end 5. So if I take point P here, another point here, all points have the same distance of 2 millimeter. Can we expect the field to be almost same at all these points here? Are you following this one? Is this something making little sense? Disha, are you following what I'm trying to come to?
Yes, sir.
It's making some sense, but I'm just trying to give an understanding of intuitive feeling of what does infinite mean, and does it even make sense? Infinite wire is impossibility. So what I'm saying, whether this what makes infinite? Infinite is basically a relative term, and I'm with some numerical example. I'm trying to give a sense that infinite doesn't mean it has to be too long. The rest of the part is not playing significant role. So even if it is something short, entire this length also, if you can theoretically calculate also, you'll find field at all this point is almost same. So I can consider entire part here, the field is almost uniform. So that's what happens, and if you have understanding, perhaps it will help you appreciate better. So let's, and this is valid in all cases. We can calculate to get a value which is 95%, we can do similar calculation for 99%. What has to be the length so that field is 99% of infinite length, and you'll find it is not too long. Okay, so we can say the rest of it is contributing only 1%. Even if it is not there also, the change in result is only to the extent of 1%. So that's the infinite. And so here also, let's in this case, let's look at this what we are looking at. And so I hope all of you have, most of you are saying you have understood. I hope we understood. What is this one? It is a long cylindrical wire. What exactly is cylindrical wire? Cylindrical wire is something like this. What is cylindrical wire? So if I have a pen like this, is a pencil. If we make the current flow along the pencil, if it is cylindrical pencil, current is flowing, it is a cylindrical one. And as long as if I take a point anywhere inside in this region, this pencil length can be considered to be infinite. Can we consider, if I'm calculating field in this region, can I take this pencil length to infinite? It can be taken as infinite. So current is flowing through the pencil or anything which is cylindrical. And if I have to calculate, now I can calculate which are the areas I can calculate field. Anything which is inside this wire and a point which is outside the wire. Any point which is outside, this radius of the pencil becomes immaterial because the current is same. So if I go outside the pencil, any point if I take outside the pencil, it doesn't matter what the size of pencil is, field is same as what it would be if it is a line, if it is a wire, thin wire. Okay, so the point is, we can proceed further from there. So this case also, I hope the next point also is clear. All of you understand that point as well. Yes. So how do you find field here? I hope the method is clear here. In this case, how do we calculate? Again, we take an Ampere loop and we take line integral. Line integral again will come into 2 pi r. Only thing what will happen, depending on what the value of r is, current impulse will be smaller. If r is become r by 2, yes, it current will become 1. Okay, if radius what we take, if this r is equal to half the radius of the cylindrical wire, then current enclosed area becomes 1/4 of the total area, current becomes I by 4, and so on and so forth. So basically what does it comes to? How do we arrive at this relationship? All of you see that it is understood, and this part remains same, only the current enclosed change. And we have done it for current to be uniformly distributed. We can also have a non-uniform distribution. We can also write as current per unit area. If I write as KR, what does this mean? So in that case, what it means, as we go away from the center, the current per unit area keeps changing. The current density is increasing. In that case also, can we calculate the current enclosed? How do we calculate current enclosed in a loop? In that case, I have to calculate what is the current enclosed within a radius equal to r. How would I calculate here? I have to, since the current density is changing with radius, I have to take a circular ring. So this also some of you can try. Maybe afternoon, if you're not able to solve, you can try and we'll go through this question as well. So any such arrangement, as long as it is symmetrical, it has cylindrical symmetry. If it is a cylindrical symmetry, we can always take an Ampere loop, which is a coaxial circle, and we can calculate magnetic field. Outside point also is clear. Now, I think yesterday we did this part, and some of you are not clear. What does this mean? Let's try and understand what does this imply. Shell and this kind of thing. So let me just try and explain this part. Something like this. Suppose this is a copper rod kind of thing, and something like this. So something like this is there. So what is the current? This is something like this. I hope all of you can follow. So what is happening if tip indicates the direction of current? So this part, this core part, current is flowing in the upward direction, and which direction, how it is flowing downward direction is moving along the cylindrical shell. So current is going like this. You can visualize the several line elements along the length of the cylindrical shell. So current is going up and basically going down. So this is something, it could have a negligible thickness, it could have finite thickness. This is a kind of arrangement we are talking about. So this arrangement is represented in form of a figure here. And let's see whether we can understand what the figure means, and we understand how to apply Amperes law here. Okay, So this one, I hope it makes some sense here. So this I have taken other way around. So if I look from the top, how would this figure look like? And can we calculate here field within the inner core? When we calculate field with the inner core, current in the outer core is immaterial. So when we take field in the inner core, if current is uniformly distributed, this particular case is identical to which case? This case is identical to this particular case. First case, if I have identical to long cylinder wire. Okay. So this part will come same. So in this particular case, if I view from the top, what are we looking at? So if I look from the top, this will look something like this. This core will look like a circle, and current is flowing into the plane. So if I have to find field at a point somewhere here, so what I have to do is become same as the first case. And what is the equation? Same formula what we have in case of a solid cylindrical wire carrying current. What happens when we take a point which is in between the two? So this current is flowing like this. So as long as, even if we are a region between this here, suppose we are at this point also, again this effect of current in this part is zero, net effect is zero. Why is the net effect of the current in the cylindrical shell is zero? You visualize what is this? This is cylindrical shell. So again, the field at any point P which lies within the core and the shell, field is only due to this part, net effect is zero. It is something similar to field inside a spherical shell charge is being zero. The reason of field being zero is that doesn't come into charge influence, the current influenced. So
if we take like two opposite points, it lies on left side and right side, right? So opposite directions of field, right?
No, basically, but yes, direction of field will be opposite. But they say if the direction of current is like this, what is the direction of field? At this point, the field will be, magnitude of field will be same. At this point like this, at this point like this, at this point like this. That's why BDL will come equal to B into 2 pi R. Okay. But is there any effect? Suppose this current is 2I, 4I, 5I. If I change this current, will it
No
change?
effect, sir.
So if I take a point P here, if I change this current I here, will the field at this point change?
It won't.
It won't. Why?
Because the field on that point due to diametrically opposite points is opposite in direction, so they
not in
cancel
that way. I'm thinking, see, when I change this current here, why is
okay, in the
field at
middle,
point
not
not
in the
change?
middle.
No, why it will not change? Okay, when I look at this one, first of all, as long as this is cylindrical symmetry, field lines will form a circular loop. As long as this cylindrical symmetry, field lines will form a circular loop. If I change this current here also, the current enclosed is not changing. If current enclosed is not changing, the line integral of field is not changing. If line integral of field is not changing, it means magnitude of field also is not changing. So this one, it has no effect, and this formula is same as cylindrical, same as wire current carrying element. And if we take a field, any field outside, yes, Vignesh.
Sir, is it supposed to be nu naught I by 2 pi r?
Sorry, yes, I missed the pi term here. Yes, mu naught by 2 pi r. Yes, good observe that one. It's a wire, so it's 2 pi term is missing. 2 pi r. How about field outside? Why is the field zero outside?
Current passing through is zero.
No, current enclosed is zero. And as long as there's a cylindrical symmetry, if I take a circle, concentric cylinder, a concentric circle, so every point, the field lines would be circular in shape. If current enclosed is zero, B has to be zero everywhere. So anywhere outside. And that's the reason people use, in fact, if you cut the cable of a signal cable also, TV cable, you will find outer, it is not like a shell, it's not like a cylindrical shell, but you see a wire mesh. So what is outer shell like? It's like wire mesh kind of thing. Have you some of this cut the cable? Have you seen inside? You see a thin cylindrical wire, insulation, and you see a wire mesh. The wire mesh is what? Wire mesh is acting like a shell. And why do we create current in the opposite direction? If we create current in the opposite direction, it does not create a magnetic field outside. It does not create any other disturbance. Because sometimes magnetic field may create other effect which is not desirable. So that's the reason why having, in case of DC current, I hope some of you understanding why this kind of arrangement, current going in one direction and coming back in other direction is helpful. What is the advantage of this kind of arrangement?
There won't be any.
No magnetic effect outside the cable. It cancels out the field outside the cable. So this is something just to make your, again, going through. Okay, so let me do some more thing here. Yes, Asha, some question?
So what will be the field on the outer cable, on the surface of the outer cable?
See, when we calculate field here, so you know continuous function, discontinuous function, right? So what is the field on the surface of spherical shell? Same question you tell me. Is it a continuous function or discontinuous function field in case of spherical shell charge?
So discontinuous.
Discontinuous. Look at the
So
sudden
till
change here. So we don't know which part is enclosed, which part is not enclosed. If it is really a shell of negligible thickness, so exactly on the shell we don't know. Just inside we know, just outside we know. And there's a discontinuity. But if shell has some finite thickness, then it will change in some continuous fashion. And you can do the calculation, Ashray. Are you following my point?
Yes, sir.
If the field changes within almost zero distance, it becomes a discontinuous function.
Yes,
If the
sir.
distance is finite, it becomes a continuous function. So in previous case also, if we think the thickness is defined, then it's a continuous function. At any point, it can be calculated. Okay, now coming to some more point here. Suppose what is if there's charge Q here, which is moving a circle of radius r. So this is circle of radius r, and it has a speed v. Will it create any magnetic field at the center? So will moving charge, or charge orbiting charge, or I can say moving charge, charge moving in a circular path, will it create a magnetic field at the center?
yes, sir, it's like
And
tangent.
if it, what would be, how would you calculate field at the center? Let me ask some of you. Tejas, can you tell me what will the field created by an orbiting charge at the center?
Sir, yes, it'll create field and then
Why? Tell me why. Because we have our formula for field is what? Our formula for field is what?
we
Current creates field. Our formula is for current.
yes, sir.
You write, we write this now, ideal sine theta and all.
Yes, sir.
So why would it create field?
Mm,
Give me a reason. And there's a definite reason. We have done this one, something similar in the past. Think hard. Why would it is current? Where's the current here? Orbiting charge is equivalent to a current loop.
yes. Oh yeah, I forgot.
So what was I expecting? Moment it says, moment it moves in a circular path, a charge moving in a circular path is equivalent to a current loop. And what is the equivalent current? Because you see, this charge will cross if frequency is f. This charge will cross this particular cross section f times. So total charge crossing in unit time becomes qf. So it is orbiting charge is equivalent to current equal to q into f. So in place of what is I here, yes, we can do that. So it becomes like a current loop. So why would it create a circular radius charge? Yes, it will create a magnetic field. What we need to do, we need to find equivalent current, and we can take a circular loop. What is equivalent current in the loop here? Equivalent current is charge into frequency. And frequency can be written as any other form it is given. You can write q into omega by 2 pi. It can also be written as q into frequency is what? Frequency is v divided by 2 pi. So it is equivalent to a loop having current, radius of r having current I. Now, can we write a formula for field at the center? Gayatri, can you write a formula for field at the center now, once we have defined the current? Yes, Akash?
Sir, you told we did this before, right? Where?
Huh?
You told Tejas like we did this before.
Yeah, we did.
No, see, any circular charge is current. See, orbiting charge.
This
Orbiting
gave a
charge
homework question, I guess.
yeah, orbiting charge is equivalent to current loop. That's what I said. Have we discussed this one? Orbiting charge is equivalent to current?
Yeah, yes.
So this we did. And this is again a reminder. So when it is current is I is defined, radius is defined, it's like a current loop having current I, and I is equal to Q into F. Now I can use circular loop formula. What is circular loop formula? Field is equal to mu naught I by 1. What is I equal to? I substitute value of I, which is equal to, if velocity is given, I'll substitute this form. If frequency is given, I'll substitute this. If omega is given, I'll this. So this is the value I substitute here. And this is the field what we get at the center. Okay. Now, and just try to think here, what is the Biot-Savart's formula for field? Biot-Savart follows something like this: mu naught by 4 pi. Okay. You notice here, this term IDL has same dimension as QV. Because what is I equal to? I is equal to charge by time into DL. If I take delta T here, it becomes Q into V. Okay. So in place of where this QV has come in place of IDL. That's it. It makes sense. So even a moving charge, if I look at the formula, Biot-Savart formula, I can write the Biot-Savart formula in slightly modified way. How can I write this Biot-Savart formula? See that one, can we write it like this also? So in place of IDL is equal to QV. So what you have done in place of IDL, you understand what is IDL is charge by time into DL. If I take delta T here, it becomes charge into velocity. So a moving charge also creates a magnetic field, not a different formula. What is the theta here?
I mean, sin theta is a component of velocity along the.
Basically, see the way here. What is the theta here? Theta was angle between two things. Which two quantities were involved in theta here? It was between
Current and position vector.
Position vector. So here also it will be between velocity and the position vector. So theta will be angle between what? Velocity vector.
Position.
Vector. So this also is an alternate form, but we can always convert into this form and write. So let's try and think of, we apply, take another different case and try and apply this concept here. So suppose now earlier it was an orbiting electron, and when electron is orbiting, will the field will be uniform when this is moving in the uniform speed? Will the field created at center, will it be a steady field or non-steady field?
Yes, so it's like current in a loop, so it will be steady.
All of you understand this point? The magnitude is constant and direction is constant. Whichever part it is moving, it is creating same field. And so at any instance, is the field created necessarily because of circular motion, or field is created only because of this motion alone? At an instance, see, when field is created at an instance, there's no guarantee it will go in a circular path. So this particular instance, this is the state of motion which is creating field.
Yes.
So if I take another case here, just try to understand that part. That's why I'm just trying to, this normally we don't do it, but still if you understand, it's a good point. So this is origin here. Let's say there's a charge Q which has velocity V like this. And what is where this charge is? This charge is at the point A now. At this particular instance, can we think of way of calculating field at O? So what is the V?
It will be similar to the circle one, sir, because
same thing. V at this instance. What is this below? It will keep changing. Here it was a uniform field. Sorry, here it was a steady field. Here it will have non-steady field. But at an instance, what is the value of field here? Field at O. What will the field at O? Khyati, do you think you can calculate what will the field at O?
Sir, I'll try.
Now tell me, think how would you relate these two things? So some of you have followed this point. Vignesh, have you understood?
Yes, sir. But in this case, it's not a steady field, right? So because it keeps changing.
Yes, that's why I mentioned also. That's why I did. What you have mentioned at this instance. See,
yes,
here what is happening? It is changing direction. It is maintaining a steady one. But in this case, what is happening? Yes, this. What will happen? This angle will keep on changing, and distance also will keep on changing. Here the distance is not changing because it's moving a circular path. Here the distance will change. So it will be instantaneous field. And again, I'm saying that this point is more, this comes into all my optional kind of category. Because some of you are people read from here and there, and then you have doubts. That's what I'm covering. Otherwise, this is something if you don't, normally you don't do it in the class also. So this is an option. Yes?
Sir, what about the force that causing the electron to move around it, the charge to move around it?
No, see, at this stage, that's what when we any science also, we break things into pieces. So at this instance, what are we discussing? At this instance, we are discussing only one thing. What is the magnetic effect of a moving charge particle? What is the magnetic effect of several charged particles moving together, which is called current. Force and all, it comes later. And then we see the combination. So at a time, you can discuss only one thing. So what are we talking? Which force is causing? Are we discussing that one? We are not discussing. What are we discussing? If charge is moving, what is the effect in terms of magnetic field? We should know how to calculate magnetic field at different points in the space, its magnitude as well as direction. So we have, if we have to quickly look at this in terms of so far what the focus of this topic is. So far what we have done till yesterday or till today, field due to current element. Today I have what we have done here. I am just correlating current per element, the way current element can cause field. Similar way, even a moving charge also something similar. Even moving charge also will cause a field. If moving charge is moving in a circular path, so its motion with respect to point O is always same. Hence, the field created at O is steady one. But if moving charge moves in this fashion, its position with respect to center, the distance keep changing, angles keep changing, it will create an unsteady field. But
Yes,
when it is at this instance, it is like a circular motion. I can, at this particular instance, if motion of the particle is perpendicular, or I can take V perpendicular. So whenever you take V perpendicular components, if the charge was moving like this, would it have created any field at the center? If the charge was moving like this,
no sir.
why not?
Sir, sign 0.
Sin 0. Because this becomes velocity vector and R vector, sin becomes 0. So what we understand, so we can, some of you can understand, if any angle out is moving, we can always take the perpendicular component and calculate. Okay, so two additional things we have done. I think something you keep in mind. One thing, some of those who want to understand better, what does finite and infinite mean, and where does the symmetry comes from. So I have given, some of you can try. I have done it for 95%. You can also look at what length is necessary for case of magnetic field to have 99% of the infinite value, and see you get a feel of this. And length required is not too long, because I'm going to come to something which will involve uniform field. Okay, field due to motion of isolated charge also we can do that. So Kathy, are you getting some sense of it?
Yes, sir. Yes.
As I said, till what we had done till yesterday, all of it should be thorough. Some part I'm doing today is which category it may fall into. It may fall into optional. If you understand, is good. It helps you understanding other things as well. But we are not likely to get numericals based on this in the examination typically. At least in examination. Okay. One more thing I wanted to understand here. See, suppose there are two current elements like this. So if I look from sideways, these are two current elements having same current flowing in the same direction. And if I place myself here, if I view from here, sometimes view from here gets a better idea of the field. Both current element will look like a dot. So if it is look like a dot, the field lines created by top element will be like this. Which direction? If it is dot, it will point thumb pointing towards me. Fingers are curling in the anti-clockwise direction. So this will be the direction of field lines.
Yes sir.
And similarly, if you take the bottom one also,
Same sir.
so what is happening in this case? In this region, what is happening? Fields are. What will happen to field in between the two elements? So if I take a field at this point, somewhere mid of this two wire, what will the field here?
0.
0. They will cancel out. But what happens if they are in the opposite direction? One is dot and other is cross.
They'll add up.
The middle they'll add up.
The middle they will add up. And what will happen at this point here? Will the field created by this element and this element? So this is the region between two current elements, fields are getting added. What about region outside the two elements?
They'll get subtracted.
They'll get subtracted. So what a point I'm making, if the current elements are in the opposite direction, in the region between the two, it gets added. In region out, it gets cancelled. And this region is too small. Suppose I take one element like this, other element is like this. And what is the field at this point? If the field is little far, so this distance and this distance are almost equal, both will calculate almost equal in opposite field, it will become almost 0. Okay, so this is the concept we'll use a little bit later, field between 2 and above below. So just understanding this, if they are in the same opposite direction, one is dot, other is cross, it will tend to get added up. So, and we have been talking about current carrying coils. What happens, if a coil, if there are two coils here. So if one coil is there, how is the field created due to circular coil? Field created is something of this nature. We had discussed yesterday in case of coil, if the coil is, the current is flowing in which direction, if current is flowing in this fashion, it will create a field in this direction, and anywhere on the axis direction of field is same. It is maximum at the center of the coil. As we go on, keep on decreasing. What happens if we have two coils having current in the same sense? How would the field get created? So what will happen? The field due to one coil and the second coil, both will get superimposed, and we'll have the vector sum of the two. If we draw the field for the second one also, if coils are identical, so other one also will have similar field. And if we sum it up, what will happen to field in between the region? You find it becomes almost uniform. If the spacing is small, see this is something, so if we keep some parallel circular coils at small distances, it tends to create a uniform field in the region between the coils. And this arrangement is called Helmholtz coil. It tends to create, and it is used in several experiments. So though it is not a separate topic in the syllabus, you don't have to understand what is Helmholtz coil, but I think the basic idea behind Helmholtz coil, this is something, if I had two circular coils, coaxial, both having similar orientation, what will happen to field in between the two is not a new thing. We'll calculate field due to one of them, we calculate field due to other one of them, and then we can add it up. So at any point on the axis of two circular coils having common axis, field can be calculated. Gayatri, can you calculate field at any point? How would you calculate field at any point on the axis of two circular coils? If two circular coils are there, do you recall any formula for calculation of field due to two circular coils? Gayatri, are there? Not there today. Okay, let me ask. So can you calculate field? Do you recall what is the formula for calculation of field on the axis of a circular coil?
Mu naught by 4 pi.
Mu naught by 4 pi.
2m by x cube.
2m by x cube, it is long distance, otherwise 2m r cube. Suppose I want to calculate field at this point due to the coil A, which is r distance, this is r distance. 2m by r cube, and this becomes equal to mu naught by 4 pi 2m by x cube. The distance is large, so we can calculate as long as distance is given. It will have r1 for this coil, it will have r2 for second coil, both are in the same direction, I can calculate them. But I think even before I calculate also, I get an understanding if the coils are placed here, there's reason to believe it tends to become uniform. If you look at these two shapes, it still not be completely uniform, but on the axis, it becomes close to uniform. There's no sudden change in field. And so we'll come to something like, so closer the spacing, more uniform the field is. And here also, the field also, just look at the cross section. See whether you understand.
Points, sir.
Yeah.
Is that?
Yeah. Let's look at this point. So if I take, this is something, this is cross-sectional view of the same. So if I take a vertical section, so what I notice here, one side the current is going in, if it is circular, other side current is coming out. So these are two opposite, and we had discussed earlier also, in between the fields will add up, outside fields will be opposite. So what will happen, this area field will be very weak, and here the field will be strong. So any circular, if you have several circles like this, what will happen? It will add up all the fields in this region. The field will tend to cancel here. Field will be weaker outside. Does it make logical sense so far, Disha?
Yes, sir.
So this is a simple thing, and then we'll come to solenoid. This is something I was doing for solenoid, but this is what is solenoid. What is solenoid? Let's first understand what is a solenoid. And okay, so suppose you take any cylindrical object, okay, and on cylindrical object, there's one way to the number of ways we can one way I can, this is what also I am winding wire on a cylinder. But in this case, what is happening? The spacing is large. Okay, but if I wind it like this, very close spacing. If I wind it very close spacing, how many windings I have? I made 3 windings. All 3 will be like a circle. So what makes the winding like a circle? We use the word tightly wound. If the wire is wound tightly and make the current flow, and if we keep winding like this, if a several wire out like this, if I have 100 windings, it is equivalent to 100 circular loops with a small spacing. Are you following so far? And this kind of arrangement is called a solenoid. Solenoid is on a cylindrical surface. If I wind the wire tightly means spacing between 2 loops is very small, that's called a solenoid. So we are trying to understand what is solenoid and why is solenoid important. See, how do we create a uniform electric field? What kind of arrangement is necessary to create a uniform electric field? How do we create a uniform?
Parallel plates.
Parallel plates. And here, because many experiments or many practical usage also, we need to have uniform field. So similarly, we were looking at what is necessary to create a uniform magnetic field. Wire doesn't create an. Circular doesn't create one. Helmholtz coil also creates somewhat uniform, not completely uniform. What creates almost a uniform field is a solenoid. We will understand how does it create and what the value of that field is. So what is solenoid? I hope you understood what is the solenoid. Solenoid is a tightly wound current carrying wire on a cylinder. Tightly wound current carrying wire on a cylinder. And okay. So what would it look like? This is what it looks like. Figure. So the top one is like a 3-dimensional figure, and this is a sectional view. So if the wires are wound like this, if I take a cross section, at top I'll see all the currents going in, and the bottom the current is a bottom current going in, top current coming out. So even before we start qualitative, we have to think what kind of field it will create. See, when we look at the solenoid, based on the past discussion, that's what the purpose of discussion is. See, this is something not easy to infer, but when I look at this and this radius, though it is blown up like this, we assume the radius to be small. When the radius is small, we in this region, inside this one, fields will add up, outside fields will cancel out. And inside, it will tend to become, as the spacing becomes much smaller, as we discussed in case of Helmholtz coil, it will tend to become almost uniform. So when we have solenoid, I think some of you just put the audio. Okay. So to sum and substance, 2-3 points here. What are 2-3 points here? Understanding of solenoid, I think that part is easy. Is a tightly wound current carrying wire on a cylindrical surface is solenoid. It has a carrying current I. I think some of you have whose audio is on. Harsha? Okay. So this is okay. And we use certain term called N. What does N indicate? Suppose I take a cylinder, I have taken a cylinder of length, say 10 centimeters. And we using a thin wire, I have done how many times I have wounded, and there's 100 windings. So can you tell what is the number of windings per unit length in terms of number of windings per meter? It will become, N will become 1000. It will become number of windings divided by length. Thus the term N we use here. What is N here? N is number of windings per unit length. I. Okay. So I'm not again, I think last 15 minutes was more to give you a feel why the field will become uniform here. Yes, the field does become uniform, but there's no, we don't prove it. We assume the field to be uniform and outside the field to become so small we can treat to be 0. Okay, and then yes, Akash.
So when they're like closely wound, so why doesn't the current just flow like a straight wire? Why in curves?
Anyway, why it will flow in curve? See, suppose if wire is insulated.
Okay, it's insulated.
Yeah. So basically, I'll come to surface current later. So it is insulated like this. So basically, what we assume inside the region field to be uniform. Now we want to find out. Yes, of course, the field will depend on 2 terms. It will depend on N. It will also depend on current. I want to find out what is the uniform field inside the solenoid. To find the field, we apply using Amperes law. Let's see how do we apply Amperes law. So this is cross section. We have taken a rectangular surface here. How is the rectangular surface? This is a rectangular surface. Two sides are lying along the axis and two other sides are perpendicular. Okay. So what is the rectangle? A, B, C, D. So what are you going to do? This rectangle, we are going to apply Amperes law. What is the Amperes law? We calculate for this rectangle B dot dl. And let's see which direction. Let me assume which direction, and let me assume this direction. I am assuming which direction? Anti-clockwise. If I take anti-clockwise direction, which curve will be positive? This current will be positive. So let's calculate this one. What is B dot dl equal to? I can divide this four sides into four parts. I'll calculate this is equivalent to saying B dot dl from where to where? From A to B plus B dot dl from B to C plus B dot dl C to D plus B dot dl D to A.
So current will be number of turnings.
Yeah, we'll come to that one. First, let's see, is it this part? Assume that field inside is uniform and the field is equal to B. Okay. So what is the B dot dl here between A to B? See, first of all, this part there's no field. So this part B dot dl is 0. But when it comes inside the solenoid here, what is B dot dl? dl is in this direction, B is perpendicular direction. So angle between them is 90. So B dot dl, this part is 0. Because outside part there's no field, inside part field is perpendicular to the dl vector. Dl vector is along the side of the Amperian loop. How about between B to C? Let's assume this length is equal to A. So B to C, angle between them is 0. So that will be equal to angle between them, cos theta is 0. So it will be into length. So it will equal simply B into A. And similar way, the weight is A to B 0. Same way C to D is also 0. And outside field is 0 anyway. So that is 0. So what is B dot dl for this? It is equal to B into this length A. So we evaluated left hand part. Right hand part, now we have to evaluate what is Q into charge enclosed. What is the current enclosed? Current enclosed will be, see, each loop, each dot we see here represent current of I. So I have to look at I into how many coils are contained within a length equal to A. How many? So current will be equal to what? Current will be equal to number of coils passing through length A into I. So what is number of loops passing through A?
A by length into N.
N per unit length. So the length is A, straight it becomes N into A into I. Okay. So that's the value and we equate. So what we get here, B into A is equal to, sorry, mu naught is also there, mu naught and A into I, or what is B equal to? Mu naught and I. So that's a simple formula which is there for solenoid. Field inside the solenoid, and what we have calculated, we have taken this, we didn't choose, let's say this is when any value of some arbitrary length R. So we have this formula what you derived, it is independent of distance of the point. So I have calculated field at this point. It is independent of distance R. So anywhere between this solenoid, the field is same, which is equal to mu naught Ni. And that's a very simple formula, but this formula is used very often. A very common formula, mu naught Ni, N being number of turns per unit length, I is the current. That's a uniform field inside the solenoid. But this uniformity, if the solenoid is something like this, the solenoid is something like this, and this is cylinder part, uniformity will be there in the central region, not in the near the end region. Because it will tend to, from here, the field lines also, you notice from here, they are parallel. When you go to the end, they'll start flaring out. The field will decrease. So this is in the interior region. So where is this field? The field is in the interior region. What we do, what does interior region mean? It depends on the radius. As we discussed, if anything which is the distance is something like even 2-3 R, even 2-3 R also is long distance. So if radius is say 5 millimeter, so 3 times radius also will be 15 millimeter. So anything which is within 15 millimeter and all would be taken as an interior region. And we don't actually, that never ask that what is interior region, but you need to understand this would be uniform in the central region of a solenoid. As we come closer to the end, field becomes lesser. Okay, is there any other way to calculate field? See, suppose I have to calculate field on the axis of solenoid. Can I calculate field on the axis of solenoid based on the known principle we have so far?
Yes, sir.
They are circular loops. They are nothing but circular loops. Is it not? So can I apply the formula of circular loops and calculate field on the axis of a solenoid? So this calculation was done on certain assumption. So can we do even using very basic approach? So
Yes,
thus
sir.
I will not do that calculation, but something like this. So suppose I want to calculate field at point P. This is a kind of this. I want to calculate, this is cross section of a solenoid. There's some point P here. I want to calculate what is the field at this point. So what I can do, if I take a small length of a solenoid, what is the length of the solenoid taken? We have taken a length dx. Can this be treated as circular loop? Yes, it is a circular loop. What is the current the circular loop will carry? This circular loop will carry current equal to, what is the current here? Number of loops passing through length dx. How many lengths? N into dx into I. That's the current. So if I take, so basically what I can do to calculate here, this derivation is not necessary, but some of you are interested can try this derivation. To calculate this field also, I will divide the whole solenoid into several small pieces of length dx. If length dx, this is the current I. Then I can write the value of field due to this element at point P. What will d be equal to? d be equal, I use the formula for circular current element, point being on the axis. That comes equal to mu naught into current into a square, but this is a formula. You get the formula, and then we integrate. So we have done something similar. Even x also I can write in terms of this angle theta. So what is x equal to? If radius of solenoid is a, tan theta is equal to a by x. So again, I can write even x in terms of theta, and we can integrate. When we integrate, angle theta will vary from this angle to this angle. I'll just give the result. So suppose solenoid, I'm finding a field at point P here. This P, find P, how do we define position of point P? With respect to the axis, one end is making angle theta 1, and the second end here is subtending angle theta 2. So what is value of field? B is equal to mu naught Ni by 2 into cos theta 1 minus cos theta 2. What happens if it is a very long solenoid? What will be cos theta 1 and what will be cos theta? What will be theta 1 and what will be theta 2? If solenoid is very long, what will theta 1? If this is very long here, so what will happen as the length increases, theta 1 will keep on decreasing, and theta 1 will tend to 0, and theta 2 will tend to, because both are measured from the same direction. So theta 2 will tend to 180 degree. If theta 2 went to 0, theta 2 went to 180, it reduces to same formula mu naught Ni. Okay, similar way, if I have to calculate, so now suppose I take point P here at the end of the solenoid. So you have a long solenoid. I want to calculate field on the axis of solenoid at the end point. At this the point P. Can we find theta 1 and theta 2 for this point here? From same line, this line, what is theta 1? This point, what is theta 1 and what is theta 2? Theta 1 is point connecting to one end and connected to other end of the top end of the solenoid. So again, if you look at the figure, try and understand this figure. This angle is theta 1 and this angle is theta 2. So what is theta 1? If I take the point P at the end of the solenoid, theta 1 becomes equal to 90, and if it is long solenoid, theta 2 becomes equal to 180. So in that case, what is the field at end point of a solenoid? Field at the end point of the solenoid is mu naught Ni by 2. see that we can do some more numericals to see whether he can apply this. See that the question we understand and try and solve this one. Length of solenoid is 1 meter, diameter is very small. Diameter is very small, it means its length can be taken as long length. So wire is wound over 2 layers. What will happen in the opposite direction? Let's try and understand. If you have a solenoid, if wires are wound like this, if you see from end, wires are going like this. So if we curl our finger, wires are wound in a particular direction. This creates field using right hand rule, one direction. If I reverse the direction the wire is wound, the direction of field also will reverse. So this question is about flowing in 2 layers in the opposite direction. It means the field also which gets created are in the opposite direction. This question is fairly simple. It is based on if 2 layers of windings are there, the field will get created also in the opposite direction. One will be mu naught I into I1 minus mu naught N2 into I2. Why we have minus sign? Minus sign when they are opposite direction. So that will be equal to in this particular case. And what is value of N here? Due to first wounding 2 layers. So number of turns. So basically what does 2 layer mean? If I look at the previous one, figure also not alright. 2 layers, just 1 layer, and the second layer is something like this. And if it is opposite, this is dot, that this will be cross, and this is cross, this will be dot.
If it's opposite, only the direction of field will change, right?
Direction of field will change. Nothing else, because that's all the same. Direction of field will change. So where they have opposite direction. Had it wound in the same direction, we would have created field in the same direction. So when I look at the cylinder, I understand the top part wires is coming towards me. So if I use right hand thumb rule, in this particular case, field is created in this direction. This is the direction field created. Just put your fingers also, lower side of the finger should be going in and upper side finger should be coming out. If you use that direction, what you find is the direction is towards right. But if I have upper layer, they have one more layer which is in the opposite direction. So if currents are flowing in the opposite direction, fields also in the opposite direction. Right? Huh?
We can subtract the ends, right?
We can subtract, that's all. It's a linear, it's along the axis. So that's why it's simple subtraction. But what is N1 here?
50.
No, first one is inner layer has 50. No, N is not number of turns. N is number of turns per unit length. Number of turns are 50.
500.
Divide by point. That becomes 500. So N is number of turns. And what is N2 equal to? N2 is equal to 400. So if you write the final, what should be the answer? Mu naught 500 into opposite direction of 3. So minus 400 into. That's the field.
So what do they mean by strength of the current?
What it does mean by the?
Strength of the current.
Guess, is it difficult to guess?
Current only, that's it.
Current only. Magnitude of current, strength of current. Yes, mother, it's a really odd word, but not difficult to figure out. But it doesn't have any special meaning. But if you're thinking it signifies something special, no. It doesn't specify. Just saying the magnitude of current. Strength is an odd choice of word, but we can still infer. So this is my magnetic field mixer in the middle of the solenoid. Middle of the season in the central region of the solenoid. So this straight away you can calculate. Okay, so one small thing left is called toroid. Maybe I'll do in the evening session. This two small things, toroid and a current sheet. So I think next session, 10 minutes I'll take to explain toroid and the current sheet. Okay, so I'll end the session here. So time is super, but these two small parts, I think I have to do it today in the evening session. So anyone has any other query so far?
Sir?
Yes?
Sir, I have a doubt in the inside you have uniform field and outside they subtract in the Hermes coil in the beginning.
Okay. Is there a theoretical proof? There's no theoretical proof.
Yes, sir.
So what I was building at, why we explained something like this before? Do you see some relation between this and that? What does this indicate here? There we are drawn if there are two fields. What will happen? So if two coils are kept, how the field will be? The field resultant field becomes something like this.
Sir, the current is flowing in the opposite direction, sir, in both the coils.
In this particular case, see, when I have drawn something like this, what does this indicate? Had the directional field been opposite, they would have got subtracted. In this particular case, both are in the same direction only. Then only field will add up.
Like it's both clockwise or both anti-clockwise. Both clockwise or both anti-clockwise, like that,
yes,
right, sir?
Yes. So this one, so does it make some sense if we have two coils, one coil, how does it field create? It's a one coil creates field like this. And second coil also, if it is identical radius, identical everything, identical coil, that also will take identical shape of the field, but only thing it will get shifted. So how do you find field in this region? At this every point, I will take the sum of these two. So how would the shape come? Something like this. It will dip, but if the spacing is small, it creates a, does it give a feeling? It will create a uniform field.
Yes, so like if they're very close to each other, both the graphs will kind of superimpose.
And does it make some logical sense that outside the field will cancel?
Sir, I didn't understand why will it cancel. It's still in the same direction, right, sir?
No, that's why I think that's why I started with the previous question. What will happen here? What did I write here? Why they are cancelling here? They are in the opposite direction. What will happen to this region? Think of it. If one element is going like this, other element is going like this. So what will the field at this point do to both of them? One will be due to this current. It will be in the left direction. Due to this current, this will be in the opposite direction.
But in the derivation for solenoid, why are we writing it as 0, sir?
Yeah, it is. See, the derivation of solenoid, there are two ways of looking at it. What are two ways of looking at it? Is there clear proof that it becomes uniform outside becomes 0? No. Only there is a indication that field becomes added up here and it becomes very weak here. So if I do a theoretical calculation, assuming it to be 0 and this to be large, and I check my calculation, how does it tally with the actual experimental value? And it is found with this assumption also, the actual value is not too far off. So we take that one as a correct one. I think I'll cite one incidence, power of averages. Say, some of you might have read the first time or maybe into an initial phase when nuclear tests were being done. So nuclear test, they wanted to get a study of when we have a particular kind of nuclear explosion, what is the kind of energy which is released. So there's very nice anecdote about it. So they have all kind of measuring devices to measure various parameters so that energy release can be calculated. Because then only we have, and then they see theoretical model and they see whether theoretical model is matching or not. So there were a number of scientists, it's a big event, number of scientists were gathered in an observation room somewhere near to the site where they were safe. One of the scientists used something like confetti. So as the explosion went off, he dropped the confetti, and based on that confetti movement, he made some estimate of energy removed. What is the energy being released? He did some rough calculation. And later on also, when they, with all sophisticated measurement, they found what is the energy released, his assumption was close to correct. So that's what I think is something you have to understand. In case of solenoid also, there is something similar. To say, okay, this side the fields are getting added up, it may become uniform. Outside it will become very less. So what happens if I take it as 0? Would that assumption be too wrong? Of course, it will not become 0. But if I do with that assumption, if I calculate field inside and apply Amperes law, is the actual field matching up with the observed value? And finds it is matches. So we know there's no proof, but this is based on what you call intuitive feel and some degree of approximation. And for approximation, there's only logical explanation, there's no proof. And it does match up and we take it as it is. That's the reason I spent so much of time going through the background part. Because there's something, there's no very clear logical evidence why it has to be taken as 0. But if there's something, if you look at this, there's a tendency why it will become weak. And it's, when we talk about weak, it is not 0, but it's much, much lesser than field inside. So relative terms, if I ignore the line integral for the outer line, my overall line integral for the loop doesn't get altered much. So Vignesh, you are following what I'm saying now?
Yes, sir.
It cannot be viewed from purely mathematical angle. It has to be viewed from understanding angle as well. It has to be
Yes, sir.
viewed from logical angle as well. Logical and a good approximation. Okay. Okay, then, so we'll end the session here. And again, if there's something there doubt, we'll continue with the same tomorrow.